All right, today we're diving deep, like really deep, right into the heart of the atom itself. We're going to try and wrap our heads around one of the most powerful forces we've ever gotten our hands on, nuclear energy. So let's get into it.
Seriously, think about that for a second. How can something so tiny, something we can't even see, create the most immense energy we've ever witnessed? It's a wild question, right? And the answer? Well, it's hidden deep inside the nucleus of an atom. To really feel the scale of what we're talking about, I'm just going to throw a number at you.
There it is, 20,000. Right now, that probably means nothing to you. It's just a number on a screen. But trust me, in the world of nuclear physics, that number, it's huge. It represents a truly terrifying amount of power.
That's 20,000 tons of TNT. That's the explosive power of the single atomic bomb that fell on Hiroshima in 1945. All that destruction came from tinkering with particles so small they're almost theoretical. So the question is, how on earth is that even possible?
Okay, so the secret lies in a fundamental rule of the universe. It's a hidden relationship, a secret handshake between mass and energy. And this is where the real magic and the unbelievable power truly starts.
The key idea we need to get is something called binding energy. The easiest way to think about it is like the universe's most powerful superglue. It's the energy that holds the nucleus of an atom together, fighting to keep all those protons crammed in there when they're desperately trying to push each other apart. But where does all that energy even come from?
And here's where it gets really weird. I mean, it's a total mind bender. If you could somehow take a nucleus, put on a scale, and then take all of its protons and neutrons out and weigh them separately, the separate bits would actually weigh more than when they're all stuck together. It's bizarre, right? So where did that little bit of missing mass go? Well, that's the secret. It didn't disappear. It was converted into that immense binding energy we were just talking about.
And this is the moment for probably the most famous equation in history, E = mc². That E is the energy, that m is our tiny little bit of missing mass, and the c², that's the speed of light, squared, which is, let's be honest, a ridiculously huge number. What it means is that even the teeniest, tiniest sliver of mass can be converted into an absolutely staggering amount of energy.
And that brings us to the whole point of this. The bigger, heavier elements, we're talking things like uranium, they have a much larger mass defect. This means they've got way more of this binding energy packed inside. So if you could just figure out a way to, crack that nucleus open, all that stored energy is just going to come flooding out.
So the big question is, how do you do it? How do you actually split an atom to get that energy out? Well, there's a name for that process. It's called nuclear fission.
Think of it like atomic demolition, but on a ridiculously small scale. You start with a big, kind of wobbly nucleus like uranium-235. Then you shoot a tiny little particle at it, a single neutron. Bam! The nucleus splits apart into two smaller pieces, in this case, things like barium and krypton. And in that moment of splitting, that binding energy is released.
Now, the energy from just one atom splitting is, well, it's about 200 million electron volts. I know, that unit probably doesn't mean much to you. But the key isn't splitting one atom. The key is what happens when you do this to trillions and trillions of them at once. That's when the numbers get astronomical. But the real secret sauce is how you get that to happen.
Look, splitting a single atom is a cool party trick for a physicist, I guess, but it's not going to power a city or create a bomb. To do that, you need a cascade. You need a domino effect. You need a chain reaction.
This is how it works. It's literally like knocking over dominoes. You hit one uranium-235 nucleus with a neutron, and it splits. But when it splits, it doesn't just release energy. Crucially, it spits out 3 new neutrons. Now, those 3 neutrons can go on to hit 3 other nuclei, and those 3 split and release 9 neutrons, which then hit 9 more, and then 27, and on and on and on. It's exponential, and it happens in a tiny fraction of a second. That runaway growth is what makes this whole thing so incredibly powerful.
Okay, so once you kick off this chain reaction, you hit a massive fork in the road, a critical choice. Path 1, you let it run wild. Path 2, you tame it. And that choice, well, it's the difference between a weapon of mass destruction and a source of clean energy. So let's look at those 2 paths. The first one is an uncontrolled reaction. The goal here is simple. Release every last bit of energy at once. You want that exponential cascade to happen as fast as humanly or physically possible. The result? An atomic explosion. But then there's the other path, the controlled reaction. Here, the goal is totally different. You want to release that energy slowly and steadily.
So, out of those 3 neutrons that get released every time an atom splits, you only let one of them go on to hit another atom. It becomes a stable one-for-one reaction. And that's how you get a nuclear reactor.
So how do you actually do that? How do you tame this beast of a reaction? It really comes down to 3 key pieces of the puzzle. First, you need something called a moderator, like graphite. Its job is just to slow those speedy neutrons down to the perfect speed for fission. Second, you have control rods, usually made of something like cadmium. These things are like sponges for neutrons. They just soak up the extra ones. By moving these rods in and out, you can dial the reaction up or down. And finally, you need what's called a critical mass. You just need enough uranium packed together in one place so the chain reaction can keep itself going.
When we discovered fission, it's like we were handed a new kind of fire. One that could either light up our entire civilization or burn it to the ground. And that really brings us back to the human side of all this science.
135,000. Let that sink in. This isn't some number from a physics equation anymore. This is a human number.
Because that is the reality of an uncontrolled chain reaction. The bomb in Hiroshima, it wasn't just an explosion. It was the physical manifestation of that exponential growth we talked about. It wiped out more than 2/3 of the city's buildings, and the human cost was just staggering. It's the ultimate and most tragic demonstration of what happens when you just let this incredible power off the leash.
And so, that leaves us with a really heavy question, doesn't it? We figured out how to unlock the power of the atom. We hold the key. But can we actually be trusted with it? The science behind it all is, well, it's kind of beautiful in a way. The power is undeniable, but it puts a massive, almost unthinkable responsibility on our shoulders. Understanding the how is one thing, but deciding the what for, well, that's a challenge for every single one of us.